The chloride anomaly is our topic. Okay? An anomaly is an exception, an unexpected outcome. Okay? The reduction table is built based off this hydrogen reference. Okay? We don't have the zero reference on the board, but your table has a zero reference, and everything is placed by hooking up a half cell to the hydrogen. The hydrogen is given the zero, the other cell is given whatever is red. Now, when you build this table, we should get strongest OA on the top left and weakest OA on the bottom left. Okay? But there's a couple times by comparing against hydrogen that the table makes the wrong prediction. For your diploma, they're going to ask you about this one exception. Okay? So when the only reducing agents present are, okay, so the OAs don't matter, but when your RA list has chloride and water and nothing else, we get the anomaly. So I've got a snippet of the reduction table. So when we have water present, we have chloride, and then we have a third half reaction to consider, the chloride-water pairing. So when we have those three labeled RAs, our table would tell us water should be the best reducing agent, but it's not correct. There's an anomaly. You need to identify chloride as the strongest reducing agent, not the water. Okay. So it's something to watch out for. You should be expecting it once on a unit test. You should be expecting it once on the diploma. It's not going to be labeled as the chloride anomaly. You have to recognize it within a question. Okay. It does not matter, again, what the OAs are. So you might have a list. Maybe you have silver ions. Okay. You've got H+ ions. And then you've got chloride. Okay. Maybe there's hydrochloric acid, which gives you H+, Cl-. Things are aqueous. So you include water on your list. Okay. You would do your labeling just like normal. You wouldn't think of the chloride anomaly yet. Okay. That's an OA. That's an OA. Chloride's an RA. Water's an RA. This pairing's an RA. I think I got them all. I'm just double checking whether H+ and water is an OA. And it's not on our table. So you'd have a list like this. You'd find the best OA, excuse me, just like you did before. So silver versus H+, silver's higher. That's the strongest OA, nothing new there. You move on to the RA side, like, oh, I've got these three. Your brain has to go, oh, the table is saying water. It is an OA. The table saying water is the strongest, but this is wrong. We have this exception. You've got to grab chloride. That's how this is going to show up. And it can be easy to miss, but if you're looking for it on an assessment, you can maybe identify it correctly. Okay. Unfortunately, many of you might miss it and go silver and water and write out those half reactions. Okay. So that's the anomaly to watch out for. Okay. I'm going to continue along, and this theme is kind of electrolytic cells and wrapping up all of our cells. It's the second last lesson. Plating. So we're going to look at one application. At the end of this lesson, I'd suggest you maybe take a look at your textbook. The Nelson textbook has a lot of examples, applications. I'm only going to do this one. Aluminum is, the production of aluminum is a nice application to look at. Now the chloro-alkyl process is the electrolysis of aqueous sodium chloride sometimes called brine or salt solution. Okay. And from this, you can make chlorine, so that'd be the diatomic. Okay. Now you can sell chlorine. Okay. It's used as to make bleaches, a disinfectant. During COVID, you couldn't make the stuff fast enough. Okay. You can make hydrogen. Okay. You can sell that as a fuel. Okay. And you can make sodium hydroxide, and that's a really common industrial base. It's the #1 base any high school is going to use. Okay. Now, when this cell, electrolytic cell is run, you can take sodium chloride. It's going to react with a couple waters, so 2 sodium chlorides react with 2 waters. You'll make your chlorine gas at the anode, so you can collect that and sell the chlorine, and then at the cathode, you're going to get a different gas, so the gases nicely separate themselves at different anodes, and you're going to get the hydroxide at the cathode as well as the bubbling hydrogen. Okay. And again, you're going to go and all of these are products that you could sell. Okay. Now, my challenge for you is to see if you can predict the chemistry. You've got the answer. Okay. You've got the full reaction. Can you predict this? And you'd be predicting the net. Okay. What is the best OA? What is the best RA there? Find the lowest common multiple, sum that up. Okay. And your answer again will drop out any spectator ions. You'll know you're right if it matches the products listed. Okay. And in a few minutes, I'll build a list, label the strongest, and you can double check whether you did this, analyze this industrial process correctly. Fine. So with voltaic cells, you can just find the 2 half reactions. Electrolytic, you've got to make your list and find the best OA and RA. So you're just looking at the circled reactants. You should have sodium ions on your list. You should have chloride ions on your list. Okay. They're aqueous, and we have water listed explicitly as one of our reactants, and that's it. Don't put the products on your list. Okay. Okay. So you're going to keep working, and shortly I'll summarize what is the best OA at the cathode, what is the best RA in this electrolytic cell at the anode, and I can net this up. So hopefully everybody's been able to label their list. So sodium ions are an OA, chloride is an RA, water can potentially be both. We've got a pairing, and then we have to watch out for other pairs with water, but our table, we don't have any. We don't have oxygen to go with the water, so the 0.4 volt half reaction doesn't work. We have water weight at the bottom with sulfate, but we don't have sulfate. So that's everything you'd have on your list. So the strongest oxidizing agent at the cathode between sodium and water, water in the left-hand column is above sodium. And sodium's way down at the bottom. So water is our strongest oxidizing agent. So 2 water plus 2 electrons is going to give us hydrogen gas and hydroxide ions. Just double checking all my coefficients, 2 waters, 2 electrons, 1 hydrogen gas, 2 hydroxide. Okay. Then we have to move on to the strongest reducing agent. So you compare chloride, water, and chloride. chloride, water, and chloride. And this should ring some bells. We've got that list that we just did. Okay, so this is another example of what the chloride anomaly would look like. If you didn't realize about the chloride anomaly, you would select water again, but it's incorrect. You need to select chloride as the strongest reducing agent. So 2Cl minus aqueous, I'm grabbing that chloride half reaction, is going to make chlorine gas and spit out 2 electrons. Okay. To net this up, the lowest common multiple of electrons would be 2. They cancel out. We don't have to scale either up. So 2 water plus 2 chloride will make our hydrogen gas, our hydroxide, and our chlorine gas, okay, which is what we expected, except it's correct. We just have sodium ions are a spectator ion. They're not gaining, they're not losing, and that's why they didn't show up at the bottom. Okay. We can know whether this happens or not. We should know that this is not spontaneous. Okay. How do I know this is not spontaneous? I grew up in Nova Scotia by the Atlantic Ocean, and there is salt in the Atlantic Ocean. There's water in the Atlantic Ocean, and I know there's not chlorine gas and hydrogen gas bubbling out of the ocean spontaneously. Okay? So I have that visual. The chemistry should also tell us it's non-spontaneous. Water is minus 0.83 volts. And I'd want to subtract the best reducing agent, which is chlorine, 1.23 volts. And when you do this subtraction, it's going to be negative. Hopefully I did my mental math right. I got minus 2.19 volts. Sarah can tell me if I'm right. Okay. So that is this example. It both covers a industrial example and covers what the chloride anomaly would look like. Okay. The fact I put in sodium ions was trivial. It didn't matter the OA that I threw in. Okay. One last electrolytic cell example, electroplating. This is done a lot industrially. It makes cheap products. Okay. Today, unfortunately, I think we're all guilty of it. We like things that are inexpensive. Maybe 50 years ago, you'd buy something that was pure metal. It was solid. Today, a lot of things are plastic underneath and metal on top. Okay? Now, it can be very advantageous to electroplate. Okay? A lot of metal things, maybe a stool, has a coating of a metal on top. You'd find that a whole stool is probably not chrome. Okay? A lot of shiny stools, shiny desks are chrome plated. Underneath, you could put a cheap metal or plastic, and you can put on top the metal you want. Okay? You can gold plate things. Okay? Maybe you don't want jewelry that is 100% gold. That's really expensive. You plate gold on top of a ring or silver on top of a ring. So that's what we want to talk about in this last example. What does electroplating look like? So I have a small, simple silver electroplating setup. You're going to draw this, and we're going to talk about the chemistry. Where's the OA? Where's the RA? Why is it so important the battery is set up with a certain polarity? So hopefully you have this diagram down. We'll start understanding what's going on. It should seem maybe a little weird. We're used to seeing maybe a lead electrode and copper ions. Different metal-metal ion combinations. But here we don't have a different combination. We've got a silver electrode, we've got silver ions. We're ultimately just transferring the silver electrode to ions, and then those ions are going to form on the other side. Okay. I'm going to skip making the list. Okay. But if you made the list and you identified the strongest oxidizing agent, which is going to react at the cathode, that's going to be your silver ions. Silver ions are a pretty good oxidizing agent. They're pretty high up in our strength table. So silver ions is the best we have. They'll gain an electron and make elemental silver. And that E0 reduction is 0.8 volts, a positive 0.80 volts. Okay. The best reducing agent, which is going to react at the anode, is we got silver ions, they're an OA, we got water and elemental silver, and the elemental silver is the best reducing agent that we have. It's better than the water. Water is a worse reducing agent. This is not the chloride anomaly. We're leaving that behind. So the anode, elemental silver, will make silver ions and an electron, and that's the same half cell, same half reaction. So its reduction potential is the same numbers. Okay. So the E0 cell, okay, under standard conditions would be 0 volts. So it's not spontaneous. It doesn't happen on its own. It just needs a little push. It needs any positive voltage, and you'll make the electrons move from one side to the other. Okay. Any positive voltage is spontaneous. Okay. So what's going on? Okay. We want to make elemental silver, produce it at the cathode. Okay. We want that to be at the spoon. We want to cover the spoon, which is going to be our cathode, in silver. So what polarity does our spoon side need to be? So we looked at electrolytic cells. Hopefully we're here for a lab. It's one of our differences. Yeah, it's negative. The voltaic cells had positive cathodes, but the electrolytic have negative cathodes. So our electrons are drawn in. We've got the negative side. The electrons are coming out and going to the spoon. Okay. The anode side is positive. So both the battery side that is positive where it's been labeled, and that's a positive electrode. So that whole side is positive. The right-hand side is negative. Okay. Our spoon is our cathode. Okay. This. Okay. Okay. The electrons don't really want to leave the silver at the anode, but the battery will rip them out, force them to be lost, forced oxidation, okay, so they can be gained at the cathode. So our chunk of silver is going to react. So there's our anode. Here's our anode reaction. Okay. So the silver is going to react. We're going to make silver ions. Okay. So we've already got our silver being produced, labeled in our diagram. So that's all anode. The cathode takes those same silver ions from solution, is going to react them at the cathode and cover that whole cathode in silver. Okay. Again, if we put a spoon in, it's going to cover this whole spoon in silver. Every bit of the spoon that's under the water. So you can't have half the spoon sticking out unless you wanted that. Okay. Maybe you just want to plate the bottom half of the spoon one color and the top half the other. You could put it in 2 different cells. Okay. And if you put half the spoon above the water, that wouldn't plate in one cell. Flip it upside down, put it in a different cell. You could plate the other side a different color. Okay. So you just need a slightly positive voltage. Okay. Over time, you will run out of the silver electrode and you'll have to replace it over time. Okay. So the same type of chemistry is how you might electroplate the kitchen taps that are in your home. Okay? They're probably electroplated. Don't do this, but if you took a knife to the kitchen taps and scratched them up, you'd probably find a plastic or a cheaper metal underneath. Okay? Your parents will be livid at you, so don't do it, but that's what you'd probably find underneath. Okay? 50 years ago, you'd find that the taps were all pure metal, way heavier, way more expensive. So it's kind of a trade-off between, it's a cost-benefit trade-off to put something cheaper underneath. Now, companies making taps, imagine an Olympic-sized swimming pool. That's your electrolytic cell. And there's a big long bar that's your cathode, and there's 20 taps hanging down into solution off that cathode bar. Okay? They're going to do this in large scale. It's not going to be a little beaker like that. Okay? But you could fairly easily set up your own electroplating setup. Okay. So that's our second application. So we looked at the chlor-alkali process. We looked at electroplating. They're both non-spontaneous. One happened to have that one anomaly you have to be familiar with. So that's most of the electrochem unit. You're going to practice shortly. And I just want to go through the list that I'm supposed to teach you that the diploma is going to write the questions based on, and this is how any teacher is going to design their test. Okay, this is what the government says I'm supposed to teach. Okay, and we've done most of this, but this is worth, if there's any of these things I go through that you're unsure of, you should be asking your teacher to clarify. So define anode, cathode. We've talked about those a lot. Cations, anions, that's the movement. Okay, you've hopefully touched a salt bridge in a porous cup in the lab. You need to know about conductive solutions, electrolytes. The external cell is the wire. Okay. Power supplies are in electrolytic cells, a battery. Okay. And you need to know about voltaic and electrolytic cells. So we've covered all that. I've mentioned a few times, it's a specific outcome. You should know the similarities and the differences between voltaic and electrolytic cells. Like, it's not a secret that, that's going to be on your diploma. It's one of the outcomes in this course. Okay? Probably on your test. Predict and write half reactions that occur at each electrode in an electrochemical cell. Okay? We've done lots of that. This word electrochemical is a big catch-all for everything. An electrochemical cell just means electrons moved in a cell. Could be spontaneous, could be non-spontaneous. But sometimes students will confuse that word electrochemical with electrolytic. Electrochemical is your voltaic and your electrolytic. Okay. Electrolytic is the non-spontaneous. Okay. We just today did the recognize that predicted reactions don't always occur. Okay. You've got the chloride anomaly. So the production of chlorine gas from brine. Okay. So that's a recent check. Okay. Explain that the values of the standard reduction potentials are relative to hydrogen. That was the lesson where I changed the reference. You should be able to change the reference. You shouldn't be surprised when that's on a test or diploma. Calculate cell potential. We've done that who knows how many times, maybe 20 times. Okay. Reduction potential at the cathode minus the reduction potential at the anode. Okay. Predict the spontaneity or non-spontaneity of redox reactions. So that's a while ago. Right? If the OA is above the RA, it's spontaneous. If it's the other way around, it's non-spontaneous. Okay. And we've got one thing left to do, which is not going to be right now, but I haven't covered 80B2.8. We're going to do some physics in our last lesson. We're going to calculate the mass of elemental metal that is made, or whatever the half reaction made. Okay, amounts. Okay, that's moles. Current and time in a voltaic or electrolytic cell by using Faraday's law and some stoich. So we're going to answer questions like, what if you hooked a battery up for 45 minutes and that battery delivered 1 amp? Okay. We're going to use that time and that current to figure out how many moles of electrons transferred, or our reduction table can tell us the ratio between electrons and whatever is plated. And we'll figure out how much mass of maybe silver is plated in an electrolytic cell. So hopefully that helps your studying for both the unit tests and your diplomas. Okay? Realize this is just the second half of this unit. Okay? There's a separate list that we went through for the first half. That was like balancing with oxidation numbers, knowing about oxidation numbers, knowing about oxidation reduction, OAs, RAs, being able to do titrations.